We've talked about differential rate laws. They're just usually called rate laws. So this PowerPoint is going to be about integrated rate laws. And the key difference, as you'll see, is that integrated rate laws have a factor of time in them, and differential rate laws don't. So if you want to know how the rate changes or concentrations change over time, you have to use the integrated rate law. As a refresher, this is the format for the differential rate law, the regular rate law, and that simply follows the rate as a function of the concentrations of the reactants. It doesn't say anything about time. And so how you get from a differential rate law to the integrated rate law is you literally integrate it. Now, we don't have to do calculus or go through this, but just so that you know how it's done. This on the bottom happens to be the integrated rate law for a first order reaction. We'll go over all the different orders in this PowerPoint. Using the integrated rate law to find order of reaction is a graphical exercise. And so I want you to notice as we go over the different integrated rate laws for zero order, first order, and second order that they are all in the format of a line. So you can think of this as y equals mx plus b. And so notice that for a first order reaction, if we plot natural log of concentration of the reactant on the y-axis and t is time on the x-axis, we get a line with a slope of minus the rate constant. And so that's the beauty of these integrated rate laws, is if you plot the rate law, or the whatever the y value is, versus time in all cases, you will get a linear relationship, and in all cases, the slope will give you the rate constant. Now, integrated rate laws have look different depending on whether the order of reaction for that particular reactant is zero, first, or second. I just showed you the first order integrated rate law, and it is has natural log of the concentration on the left side of the equality. If it were to be a second order reaction, then this is the format of the integrated rate law. It's 1 over the concentration. So as in the case of all of the rate laws, if you plot, let me put the y equals mx plus b here again. If you plot the value of y on the y-axis versus time, you will get a straight line. And in this case, the slope equals k. If you remember, for a first order reaction, the slope was minus k. Now, let's say that you have this reaction, and for whatever reason, you think that it's first order. Say you don't really know. So if you were to plot, assuming it was first order, you would put natural log of the concentration on the y-axis, time on the x-axis, and you would not get a straight line. So you only get a straight line if you use the correct integrated rate law that matches the particular order of reaction. And a zero order rate law, on the y-axis, you would simply plot the concentration of the reactant. And again, the slope would give you, I'm not sure why the A is there, the slope would give you the rate constant. So here's a summary of the integrated rate laws for zero order, first order, and second order. This is a really nice little table. You may want to print it out. And you can compare to what the differential rate law would look like for each of these. And just kind of a reminder, they're all in the format of y equals mx plus b. And so if you were to plot them, either to find the rate constant k or to determine what order the reaction was, this fourth column tells you what you would plot on the y-axis to determine whether or not it's that particular order of reaction. So here's a specific example. For the chemist in the lab, creating integrated rate law data is easier than if you were working with the differential rate law. For the differential rate law, you may remember we made a table of data called the method of initial rates, and that required running several different experiments, each experiment with a different concentration of reactant. And in the case of working with an integrated rate law, you only run one single experiment. You simply monitor it for a period of time, making sure that you also monitor the concentration of the reactant over time. Then when you are finished, you have to make 3 graphs to determine the order of reaction if you don't already know it. You would have to make one graph with simply the concentration of A on the y-axis, and you'd have to then calculate natural log of A and 1 over A and make graphs with each of those on the y-axis. And the graph that gives you a line, a straight line, tells you the order of reaction. So let's just, for fun, say that we get a curve when we plot concentration of A, we get a curve when we plot natural log of A, and we get a straight line when we plot 1 over A. So that tells us right away that this reaction is second order, because the second order integrated rate law when plotting gives us a straight line. So let's go ahead and see what this particular reaction was according to this data. Here are the actual graphs. Now you can see the graph that gave the straight line in reality was when natural log of concentration of A is on the y-axis, which tells us that this reaction is first order. Here's one for you to try. If you have any idea at all how to approach, go for it, turn the video off. Otherwise, I'll walk you through this one, then give you another one you can try on your own. Alrighty, most of these finding the order of reaction, you don't even really need to write the balanced reaction out or necessarily even know what it is. There is a piece of information up here that's important to us, and that is it gives us the rate constant K. There's a really important piece of information we can get from the units of the rate constant. So if you're not familiar with the units you get for zero order reaction versus first order versus second order, I'm going to tell you real quick so you have, because they're really important to know. So if we had a zero order reaction, the units for the rate constant would be molarity per second. If we had a first order reaction, the units for K would be 1 over second. If we had a second order reaction, the units would be 1 over molarity times second, and just say the total order reaction, if it were third, would be 1 over molarity squared times second. I'm hoping you can see the pattern here. With each increase in the order of reaction, it's like dividing by molarity. Okay, so maybe that'll help you remember. Anyway, notice in this case, 1 over seconds, that's what s to the minus 1 means, 1 over second, tells us right away this is a first order reaction. That's really important to know that. And by the way, it doesn't have to be seconds, any unit of time. It could be 1 over minute, 1 over hour, 1 over year. All right, so we know it's first order. Let's go back to question A now. It's given us the initial concentration of the reactant, and it's asking us what the concentration of that reactant is after this split instant of time. So here's another big clue. If you're working on any kinetics problems, and the problem even mentions time in it, you need the integrated rate law. The integrated rate law is the only one that has the variable of time in it. So we know it's first order. We know we need the integrated rate law. So let's go ahead and write out the integrated rate law for a first order reaction. All right, so it's important to know what the symbols are. This is natural log of concentration A at any particular time you're looking. K, of course, is the rate constant. T is time. And A sub naught, this is the initial concentration of A. All right, so let's plug in everything we know. We are supposed to solve for the concentration of A at time t. So that's what we're solving for. They gave us K. They told us it was 87 inverse seconds. And we know the time. They asked us to find the concentration after 0.010 seconds. You can see your units cancel. Be really careful that the units for the rate constant and the units of time match, so they do cancel. And it changed on me, didn't it? All right, plus natural log of the original concentration of A, which was 2 molar. And that's it. That's just plugging and chugging. So let's go to the next page and see it in a little bit neater format. All right, where are we? Here we go. So when you plug through the math, you're going to get the natural log of the concentration of the reactant, which was C4H8, is minus 0.18. Now, you may have gotten rusty or may not know, you don't want the natural log of the concentration of C4H8. You want simply the concentration of C4H8. So how do we get rid of a natural log? Well, you raise both sides, raise the value, E raised to that value. I don't know how to say that right. So both sides, you use E. And E and natural log cross each other out. So what we end up is simply the concentration of C4H8 equals E to the minus 0.18. Plugging that into your calculator, you get 0.83 molar. Now I want to warn you, since this value is an exponent, it's extremely sensitive to any minuscule change in value. So if you said, nah, I'm going to round that 0.18 to 0.2, don't do it. Okay, that's going to make a huge change in your. So here's a problem for you to do. I strongly suggest, even if you don't feel confident, that you turn off the video, give it a shot on your own. Now I'm going to pretend like I was reading this as a student. And even now, after doing chemistry for a long, long time, when I read a question, I don't immediately know how to solve it. So I'm going to look for clues as I read through. It's second order. I'm going to go ahead and make little notations that might be important. And it mentions time. Again, any time you see time mentioned in a kinetics problem, you need the integrated rate law. So before you even try to figure out more about what you're doing, or at least this is the approach I would take, I'm like, okay, I need second order integrated rate law. What is it? It is 1 over concentration of the reactant at time t, and that equals KT plus 1 over concentration of the reactant initially at time 0. And let's see, what are we solving for? Wants to know the final concentration, so that's this. All right, I'm just going to, it's plug and chug again. All right, they gave us K, 5.76 times 10 to the minus 2 liters per mole minute. They gave us the time, 10 minutes. I'm going to make sure the units match, and they do. My minutes cancel. And they gave us the initial concentration of A, which is 0.2 molar. And now I'm going to plug and chug. All right, so this ending is really important because it's a very common mistake that students make. When I plug and chug all the numbers in, I get 5.576. Now do not stop here, because what does 5.576 represent? It represents 1 over the concentration of the reactant. I don't want 1 over the concentration. I want the concentration itself. So how do I get simply the concentration of A at times T? I've got to flip it. So that is equal to 1 over 5.576. And that is, whoopsie daisy, 0.179. And don't forget units. It's a concentration, so it's molarity. Alrighty, I'm hoping you're starting to get the hang of it. These integrated rate law plug-in chugs are pretty easy. The remainder of this PowerPoint is about half-lives, and we're going to derive the equation for the half-life of any reaction from the integrated rate laws. It's really easy to do. But first, to make sure you understand what half-life is. First of all, half-life is a unit of time, okay? So it will always have units of seconds, minutes, hours, years, whatever. And thirdly, the definition, it's the amount of time it takes for a substance to decrease, to be cut in half, okay? Decrease by a factor of 2. In this particular example, the half-life is staying the same for this particular reaction. That is not always the case, just so that you're aware. So half-life of a first-order reaction, which is by far what you will be working with most, and it's worth memorizing at this point that any radioactive decay is first order. So any problem that mentions radioactivity, pull out the first order integrated rate law. Now it's really easy to get the half-life expression for a first order reaction. It is simply natural log of 2 divided by K, the rate constant. The natural log of 2 happens to be 0.693. But what I want you to notice more than anything is that half-life and rate constant are inversely proportional to each other. So if the rate constant were to increase, let's say by a factor of 2, that means the half-life would decrease by a factor of 2. Makes sense, right? You got a faster reaction, the half-life will be shorter. Things will happen sooner. All right, so it's worth memorizing the formula for the half-life of a first-order reaction, but it's also really easy to derive. So if I write out the expression for a first-order integrated rate law, the form that we're familiar with, and you may or may not remember that one of the properties of logarithms is if they are subtracted from one another, you can put them in ratio form, kind of in division form. If they're multiplied or if they're added together, you can put them in multiplication form. So let me show you what I'm talking about. If I rearrange this equation so that it reads log of concentration of A, move the other log expression to that side, equals minus KT. All right, you see here now that I have natural log of A at time t minus natural log of A at time 0. Anytime you have logs subtracted from each other, you can put them in ratio form like this. Now we're getting ready to make a substitution so that we can simplify this further. When you've reached the half-life, what has happened to the concentration of A? At half-life, at each half-life, the concentration of A equals 1/2 of what it was originally. Alrighty, so substituting in then, get natural log of 1/2 concentration of A at time 0. That's from this substitution. over concentration of A at time 0. Those cancel. So now you're probably starting to see where the half-life expression comes from. And so now if we were to rewrite it, natural log of 1/2 equals minus KT, and you can flip that, get rid of the negative sign and flip this over, and that's where we get it from. Now, just to show, there are different half-life expressions for whether it's 0 order, 1st order, or 2nd order, and probably the only thing we'll be using in our class is the half-life for 1st order. But I did want you to see that the half-life for 1st order is the only one that does not depend on the initial concentration of the reactant. So half-life is set for a particular reaction if it's 1st order, regardless of how much you start with. This is some other just kind of tips that are useful when you're working half-life problems. Because fractions, a lot of half-life problems are just, the question is such that it says, well, 3/4 of the original material remains, or 75% is decomposed. And so I want you to just get familiar with these fractions. So after 1 half-life, 50% is decomposed, right? So that means 50% is left, or 1/2 of it's left. And you just keep multiplying 1/2 by itself for each additional half-life. So after 2 half-lives, 1/4 of the original atom remains. Because you start out with 50% remaining. If you take half of that, you only have 25% remaining, which is 1/4, okay? And you just keep multiplying that by 1/2 over and over and over. And so after 6 half-lives, 1/64. So I would get familiar with some of that. Work a sample problem. All right, rate constant, that tells you right away it's 1st order because the units are 1 over time. What is the half-life of this reaction? So let's write out the equation for half-life for a 1st order reaction. And then let's see what information we have. They give us the rate constant, and so this one's really easy. We're just plugging in, and so it's 0.693 over 9.2. And when we plug that in, and the answer is 0.075, what are the units here? Seconds. It's a very short half-life. For the second question, B, how long does it take for the concentration to reach 1/4 of the initial value? You could do that. There's an easy way and there's a hard way. So the easy way is if you get familiar with fractions, like I told you on the last slide. And so after 1 half-life, you have 1/2 left. After 2 half-lives, you have 1/4 left. And so that means that 1/4 is 1/4. So that means that 2 half-lives have passed. We just calculated the time for 1 half-life. So the easy way is simply 2 times the time for 1 half-life, and that would be 0.15 seconds. There, now, if you don't remember those fractions, or if you're given a funky fraction that isn't even like that, you can also use the integrated rate law for 1st order reaction, and you can find out that way. So remember, all radioactive decay reactions are 1st order. So doing it that long way, we would start out by writing the expression for 1st order integrated rate law. And then plug in what you know. This is good to realize how to handle this. But if you have 1/4 of the initial value left, okay, you can put in ratios for these initial and final concentrations. So let's put in 1, some arbitrary 1 for the initial concentration, and then it said there's 1/4 left. So either put in 1/4 or 0.25. They gave us the rate constant, 9.2, and we're solving for time. And so if you plugged all that in, you would get the same answer, which was 0.15 second. That's kind of a longer, cumbersome way, but if you can't remember fractions or the shortcut, that will always give you the right answer. All right, this is a really cool application of half-life. I'm sure you've probably heard of carbon-14 dating. It turns out that carbon-14 is a radioactive version of carbon that exists only in the atmosphere, but it gets into our atmosphere, and so every living thing incorporates carbon-14 into their living system. And so there is a certain ratio of carbon-14 to carbon-12, which is the most common isotope of carbon, in any living substance. And then when a living substance dies, they stop taking in carbon-14, and since carbon-14 is radioactive, it starts to decompose. So with any dead thing, if scientists analyze the exact quantity of carbon-14 left in that substance, it can figure out how long it's been dead. Pretty cool. So here's an example. You get a lot of fossils dated that way. First of all, the half-life of carbon-14 is very well known. It's 5,730 years, which is nice. Because of that really long half-life, we can date things back thousands of years. So, what are they asking here? This is all just kind of words. All right, so if you're talking about radioactive problems, quite often it'll say disintegrations per unit time. I want you to think of that as concentration. Nuclear chemists, instead of dealing with concentrations and solutions like molarity, instead of seeing that, they will often just use capital letter N, meaning amount, some generic amount. And so their disintegrations per minute are the equivalent of our molarity, and you can use them in just the same way. So I just wanted a heads up on that. Don't worry too much about the units. All right, so can you decipher this sentence? If the ratio of carbon-12 to carbon-14 in a living substance is 15.3 disintegrations per minute, that is the initial amount or initial concentration, okay? So now let's go ahead and look at our first order integrated rate law, and let's go ahead and plug in everything we know so far. The, quote, concentration or amount at time t is 5.22. And instead of K, we were given half-life. Okay, so don't get this mixed up. This is not little t in the equation, which is the amount of time the reaction has gone. That is not half-life, okay? We're going to use half-life to find K. So remember that half-life is 0.693 over K, and that means if you rearrange that, that K equals 0.693 over half-life. So let's go ahead and figure out what K is. All right, and that tells us then that K is 1.21 times 10 to the minus 4. And since it's a first order reaction, I know that the units are 1 over time. In this case, it's years. So here's the value of K. So I'm going to go back up here and plug that in for K. We're solving for time, which is the age of the fossil. And let's see, now we have to do plus log of concentration A at time 0, which is 15.3. All right, so if you solve all that, plug all that in, I would make yourself try to go through that. Make sure you understand what's happening because you're going to have to do it. You will get 8,890 years old is that fossil, that bone. All right, it is your turn. Okay, here is, again, carbon-14 is radioactive. It's talking about decay. It gives you a fraction. All of those are clues that it is a first-order reaction and that it is radioactive decay. So you need to have your formulas handy. So let's see, what does that involve? That's the first order integrated rate law. And let's see, the expression for half-life for a first order equation. All right, and then I would turn the video off, see if you can plug through it on your own, then turn it back on and I will work it out for you. The first thing I want you to be really careful with is they said 70% of the wood has decayed. So be real careful of the wording because how much is left? These equations are in terms of how much is left. So this can kind of be a trick. So if 70% is decayed, that means that 30% of the original material is left. And that's what you need to plug into the equation. I also should have put in that problem because you're not expected to memorize it, that the half-life for carbon-14 is 5,730 years. All right, and so I'm simply going to use first-order integrated rate law. And I know that I need to find K, the rate constant, first. And let's see, so K is going to be 0.693 over the half-life. You're going to probably memorize this number after a while. And that is 1.21 times 10 to the minus 4. Again, it is first order reaction, so the units are time to the minus 1, or 1 over time. And so I'm going to do the same thing. I have a percentage, so 30% is left. So how much did I begin with? I began with, I'm just going to say 100%. Doesn't really matter if you start with 1 over here or 100 as long as you have the right ratio left. I also know K, and I'm solving for T. And let's see, I have 30% left. Alrighty, so now I'm just gonna kind of plug and chug. And so the log of 30 is 3.401. And I'm not gonna do anything with that yet. And the log of 100, sorry about that, I'm getting messaged, 4.605. All right, so now I am going to combine both sides. And so I'm going to get 1.204, I'm carrying extra digits at this point, equals 1.21 times 10 to the minus 4t. And so I'm going to divide both sides by 1.21 times 10 to the minus 4. And by doing that, I'm going to get that t equals 9,952 years. So that's it, and that's it for the PowerPoint.